After that, specify the properties of the dataset that you want to generate. InSamples specifies the total number of data points distributed equally between all the clusters. Define the random state value as 20 to initialize the centroids. You also need to define how many features your samples would have. Fit the generated dataset into the k-means object. Specify the number of clusters you want. When you print the estimator object, it returns the label values of each data point. The labels show which cluster a data point belongs to. In this demo, you saw how to import random sample generators to create datasets. You also learned to implement the k-means clustering method for classifying data points. A large dataset can have multiple dimensions. When you have a multi-dimensional dataset, you need a lot of data points to create its representative sample. If you have to perform an analytics operations on it, the performance would be very slow and sluggish. For example, just imagine a large spreadsheet with a few thousand rows and a few thousand columns. You definitely want to trim down the spreadsheet for faster computation. To do that, you might want to drop off a few columns from the dataset without losing the information it contains, because that might lead to a wrong analysis. This is where dimensionality reduction comes into play. It helps cut down the dimensions of a multi-dimensional dataset without losing any of the data. Let's now see the different techniques for dimensionality reduction. The first method is to drop the columns which contain missing values and exceed some defined threshold value for the dataset. Data variances indicates the changes in the data value. So if there are small changes in the data, then you can choose to remove data lower than a defined threshold after normalizing it. Correlation indicates how data points are related to each other. If they are highly correlated, only one set of data points can be kept while others can be dropped. Principal Component Analysis, or PCA, is a statistical function which transforms the original datasets into a new set of coordinates by keeping the highest possible variance to ensure there is a significant loss in data. Principal Component Analysis, or PCA, is one of the most used unsupervised learning algorithms. It's primarily used to compress or reduce the data. This functionality also helps it to carry out dimensionality reduction. PCA tries to capture the variance, which helps it pick up interesting features. That's why it's also useful as a feature extraction method. In short, we can use PCA to reduce dimensionality in the dataset and to build our feature vector. In the diagram, the principal axis in the feature space represents the direction of maximum variance in the data. This slide shows how PCA algorithm works in Sklearn. Recall that PCA helps reduce the dimensions of a dataset by keeping only the significant singular vectors. Sklearn has a class called PCA. It has to be instantiated by creating an object, also called an estimator. Let's take a closer look at the signature of the class. InComponents indicates the number of components that should be retained. If this variable is not set, then all the components are retained. Copy overwrites the transformed data after fitting it into the model. It's not used frequently because we don't often need to overwrite the transformed data. Whiten simply removes the data with lower variance and improves the prediction accuracy. In this demo, you'll see how to use the Principal Component Analysis, or PCA model, to reduce the dimensions of a given dataset. Let's start by importing the PCA library from Sklearn decomposition. Let's also import the random sample generator, makeBlobs. For the sample generator, define the size of the sample and its random state values. Next, create the dataset by passing the parameters to the class instance. Here, I have selected 10 features for the dataset. The goal of this method is to reduce the number of features present in the dataset to the defined or desired low dimensional value. Let's view the current shape of the dataset. Note that it has 20 observations and 10 features or attributes. In this demo, let's see how we can reduce the number of features from 10 to 3. To do this, create an instance of the PCA class and specify how many components you want. Then, fit the x-axis or axis 1 into the model. Use explained variance ratio to view the percentage of variance explained by each of the selected components. You can view the first PCA component values using the syntax shown here. Use the transform method over the fitted data to apply the dimensionality reduction. View the shape of the reduced dataset. As you can see, the number of features are successfully reduced from 10 to 3. In this demo, you saw how to use PCA to reduce the dimensions of a given dataset. A pipeline helps simplify the process where more than one model is required or used. When you are using it, call the predict method once all the data is fit into the models or estimators. All models in the pipeline must be transformers. The last model can either be a transformer or a classifier, regressor, or other such objects. In this demo, you'll learn how to build a pipeline containing more than one estimator using Sklearn. Let's start by importing the required libraries and estimators. In this case, you have to first import the pipeline class, then the logistic and linear regression estimators from the linear model, and finally the PCA class from decomposition. The next step is to chain the estimators together. The key point to note here is that all the estimators in the pipeline, except the last one, must be transformers. The last estimator can be a transformer or a classifier. Put all of them together in a list as shown here. Now, create a pipeline object and pass the chained estimators to it. When you view the properties of the pipeline object, you can find all the estimator objects within parentheses. Now, let's view them in a sequential order. The steps method helps you to view stepwise processing of the pipeline. In this demo, you saw the libraries that you would need to import to create a pipeline. You also saw how you can chain different estimators together, view the pipeline process together, and in a stepwise manner. Once you create a model,